E bienvenido a la química. Okay, let's continue. Today, we're going to start this set of slides. We are going to look at redox reactions, or oxidation-reduction reactions. Then, we will talk about concentration before moving on to different laboratory techniques. All right, redox reactions, or oxidation-reduction reactions. Technically, most reactions involve the movement of electrons. Redox reactions, they make the electrons and the movement of electrons, the exchange of electrons, the focus of our investigation, of the formalism of studying reactions. They treat reactions as being an explicit and complete exchange of electrons from one element to another. And it's similar to, but not exactly the same as, formal charges. And this is another way of looking at reactions, another way of studying reactions and understanding what's going on, and it's quite useful. Redox reactions is more typically applied to certain classes of reactions rather than others, but you can apply it to a lot of different kinds of reactions. So first, we need to look at the oxidation number. Like I said, it's sort of similar to formal charges. It's also related to ionic charge, but it isn't exactly the same as either. Okay. So let us, we'll start with natural elements, pure elements. The oxidation number on a pure element is 0. This is a matter of definition. Okay. So the formal charge, the oxidation number on metallic iron is 0. On molecular oxygen, 0. Molecular phosphorus, that's P4, it's 0. Molecular sulfur, 0. Okay. If you look at, say, carbon, or hydrogen, or nitrogen, or mercury, okay, so long as it's in its pure elemental form, it's 0. Note that this ignores the state of matter. It doesn't matter if it's solid, liquid, or gas. That the oxidation number will still be 0. Okay. For a monatomic ion, the oxidation number is very straightforward. It's just the charge on the ion. So sodium 1+, the oxidation number is 1+. Oxygen 2-, the oxidation number is 2-. It gets a little bit more complicated when you're looking at a polyatomic species. The oxidation numbers on the individual elements have to add up to the charge of the whole compound. So for carbon dioxide, CO2, they add up to 0 because the total charge on CO2 is 0. For CO3, 2-, all of them together have to add up to 2- because that's the charge on the whole thing. Similarly, NH3, the oxidation numbers for all 4 atoms, the nitrogen and the 3 hydrogens, has to add up to 0. For NH4+, it has to add up to +1. So that means that you're going to need some way to determine what the charges on, the oxidation numbers on those individual atoms are. For fluorine in a compound, it's always going to be -1. Okay. This is related to and based on electronegativity. So for fluorine, it's always -1. So when you're looking at hydrogen fluoride, fluorine is -1. The whole thing has to add up to 0. So that means that hydrogen, in order to balance it out, has to be +1. So those are the 2 oxidation numbers. Okay? -1 for fluorine, +1 for hydrogen. For the alkali metals and the alkaline earth metals, that's the first 2 columns here on the periodic table. Alkali is the first column, alkaline earth is the second. Nice and straightforward, it's going to be related to the charge they can take. Alkali is +1, alkaline earth is +2. So going back here, Sodium fluoride, sodium is positive 1, fluorine is minus 1. Nice and simple. Magnesium oxide, magnesium is positive 2, oxygen is negative 2. Hydrogen, it's a little bit more complicated. It's positive 1 when it's with a non-metal, negative 1 when it's with a metal. Remember that a little while back I said that hydrogen is kind of a metal, kind of a non-metal, depending on who it's bound with. Well, oxidation numbers makes that kind of formal. When it's bound with a non-metal, hydrogen is acting sort of like a metal, in that it has a positive 1 charge. When it's with a metal, then it's taking on the role of the non-metal and taking on a negative 1 charge. So, remember hydrogen fluoride, hydrogen has plus 1. But when you combine it with sodium, sodium has a positive 1 charge, hydrogen has a negative 1 charge. Okay, and this is, if you remember from your nomenclature, this would be sodium hydride, whereas this is hydrogen fluoride. So even the naming makes it a little bit different. So hydrogen is positive 1 or negative 1, depending on who it is bound to. Oxygen can have 3 different possible oxidation numbers. Negative 2, or I should say there are 3 different classes that oxygen can belong to. It can be negative 2, and it's almost always negative 2. If it's a peroxide, O2 2-, then it's negative 1. And if it is bound to fluorine, then it's whatever it needs to be to make the whole compound happy. Fluorine is the only thing that can give oxygen a different oxidation number, because fluorine is just that electronegative. So, looking at different possibilities, magnesium oxide or sodium oxide, it's just nice and straightforward. For both of these, oxygen would be -2. For sodium peroxide or hydrogen peroxide, both of these, oxygen is a peroxide, that's the name, and oxygen is going to be -1. And the other possibility is oxygen bound with fluorine. Fluorine is always -1, and so oxygen is going to take whatever charge is necessary to balance out the charge of the whole compound. In this case, the entire compound is neutral. So if oxygen is just N plus 2 times -1 is 0. You solve for N is equal to +2. Bing! Okay. That gives oxygen an oxidation number of +2. And finally, the halides, with the exception of fluorine. So that would be chlorine, iodine, and bromine. Or I should say chloride, iodide, and bromide. Those are going to be -1 almost all the time. So hydrogen iodide, -1. Sodium chloride, -1. Silver bromide, -1. So you can see that this is very closely related to the charges that they prefer to take, the formal charges they might prefer to have, and so on. But when the halogens are bound to fluorine or oxygen, then their oxidation number is going to be determined by the charge of the compound. They'll take whatever number they need to take in order to balance out the total charge on the compound, just like with oxygen and fluorine. So, for example, IO4 1- periodate. Oxygen is always -2. There are 4 of them, giving you -8. And then you have the total charge on iodine. So, N plus -8 equals -1, because the total charge is -1. So the total charge, the oxidation number on iodine is going to be positive 7. Then you look at, say, chlorine trifluoride. What is the oxidation number on chlorine? Well, fluorine is -1. There are 3 of them for a total of -3. Then you have just the one chlorine. So N plus -3 equals 0. Total charge is 0. The oxidation number on chlorine is positive 3. So oxidation numbers can be difficult. They can be confusing. You're going to have to do the math. That's really all there is to it. Well, do the math and remember that long list of rules. And you're going to have to practice, practice, practice. So let's take a look at ammonium really quick. NH4 plus. Each hydrogen is +1. There are 4 of them, and a total of 4 plus. Then you have N for nitrogen. N plus 4 equals +1. The total charge is +1. So that means that N, the charge or the oxidation number on nitrogen, is -3. Now, you're going to have to remember that this is going to be affected by the subscripts for both or every member of the compound. So let's look at dichromate, Cr2O7, 2-. Oxygen is -2, and there are 7 of them, giving a total of -14. Now, N plus -14 equals -2. So N equals +12. But there are 2 chromium, so you're going to have to divide that by 2 to get the charge or oxidation number on each chromium. +6. So -2 and +6 are the oxidation numbers for the 2 different elements in dichromate. And that's where we'll go ahead and call it quits for this video. When we come back, we'll start talking about redox reactions.